So I'm about to present my poster defining an alternative pathfinding method by approaching social distancing through macro and micro level in the city. This is originally an excerpt from my architectural computation dissertation at the Bartlett, which was supervised by Ava Fatah and Petros Koutsalampos, that as a result are the two other authors of this work. Next slide. So as an introduction, I can say that the outbreak of coronavirus back in 2020, it impacted many social behaviors and also many daily activities. And this resulted in the definition of many social distancing measures, which were the kind of the measures that would keep people safe from the virus, as the virus itself, it's air transmissible. This applied to whether indoors or outdoors. Next slide. There are certain activities that for them enough social distancing measures were not actually predicted or defined. And one of these many activities that are actually daily include pathfinding and navigation in the city itself. So therefore, we should say that there's a need for a pathfinding method that can actually produce paths that could be perceived to be safe from the virus by actually navigators. Next slide. So we looked into a certain related piece of work. One is actually mobile application, and that is actually created by MIT Media Lab, which is called Safe Paths. It uses Bluetooth to actually track people and find the safest paths from the virus itself, which is done by actually tracking people, done by an agent-based model. And this is a time-based approach into looking into this matter. The other study that we were interested in was a study done by Space Syntax Limited, which is called Reimagining Urban Centers for Living with COVID-19. They aim to actually imagine a pandemic city and to devise cycling and walking paths for after the pandemic. This uses street network analysis, and it looks into a probability-based approach, moreover, which is actually opposed to the other related work. Next slide. So when it comes to pathfinding and when it comes to the notion of social distancing, we're not only interested in micro scale, but we're also interested in a macro scale. Now, when we say micro scale, we actually mean the human experience itself, as it's really important that when we talk about social distancing, we walk in the city, we navigate, it's really important to be able to keep ourselves safe. And on the other hand, we can look to the notion of social distancing for a macro scale, and by looking from above, from cities, for spatial configuration in this matter, in order to have a better response to when it comes to pathfinding. Next slide. So due to the cost and data privacy issues that are related to time-based approaches, we actually chose a probability-based approach. Based on the reasons that were actually mentioned. Therefore, that the methodology that we actually used for this project were most importantly, a probability-based approach and not the time-based one. Also, it's important to mention that the notion of COVID safe in general is a very unclear notion. And there's no certain meaning into it that what can actually be defined as COVID safe. But for one thing, we can actually say that we could find kind of paths, and we can devise a method for finding a path that could bring the perception of safety from the virus for the user or whoever was actually navigating in that path. So we're interested in the perception and not the notion of COVID safe path itself, because it's a very unclear meaning. Next slide. So now we're looking into the input, which is actually the main methodology of this study and of this research. Next slide. So when we talk about pathfinding, we were looking into a certain area of study. Of course, that this method can be applied to certain cities and certain areas, but for this study on its own, we were looking into a certain area within central London itself, especially that this is an area that throughout the pandemic, especially in 2020, had some of the highest cases because it has streets and it has paths that some of the highest flows and some of the highest populations, and many events take place here. So this area in general, from the west, it ends at Barbican Center, from the north, Shoreditch High Street, from the east, Whitechapel, and from the south, it ends at London Bridge. Next slide. So as an overview of the methodology and how it works, after actually selecting the area of study for observations and many reasons and the experimentation itself, we look into the methodology. Now, the methodology in summary, it uses street network analysis. That is a very common method used in space syntax methodology. We look into the Dextre algorithm, which is a famous algorithm that is actually used for pathfinding and finding the most efficient path. And then also we look into the extraction of selected land use of some of the most visited location types that is extracted from Google Maps API. That is actually witnessed from the pandemic, meaning that we're looking into the pieces of land use that were actually the most visited by people throughout the pandemic. And this was done by observations. Some of these land use include cafes, pubs, bars, public transport stations, and as well as supermarkets. This applied to lockdown and when at the time that there was no lockdown, and solely we were looking into the pandemic itself. And then last but not least, as a part of the methodology, but also as the last part and the conclusion and the experimentation, we were looking into validating these designated paths produced by the algorithm. And these were tested on actually humans. There were like in the last section, humans were required to actually validate the paths and take them and answer to certain questions. Therefore, the methodology at core is consisted of a series of macro scale steps and micro scale as a result. Next slide. So as a step-by-step of a methodology overview that I just mentioned, the first part includes the segment analysis from space syntax of the selected areas. So we extract certain street network access information from the selected area above mentioned. The second part is talking about implementing the Dextre algorithm, producing the algorithm itself in order to be able to draw those paths. The third part is actually extracting land use information on that certain area that is selected using Google Maps API. And the land use that was actually chosen and picked, which were the 4 land use mentioned before. And then the fourth part, what it's actually doing is that it's compiling the first section and the third section, which produces one map that has all these information, including the land use and the segment analysis. And as a result, now by step 2, we attempt to actually draw that path using the information we have. And we're attempting to find that efficient path that could bring the perception of safety from the virus. And as the last part, which will be mentioned in the next section, is the experimentation and testing on people. Next slide. So as the first part, we mentioned that from space syntax, we're looking into a segment analysis, and this produces us a segment map. After producing the axial analysis, we attempt to produce the segment analysis. This gave us a segment map. And what we're really interested to find out is the amount of integration and choice, which is the to movement and through movement that can actually be seen in these segments and in these streets. So we looked into the 600 metric radius level of it because we're interested in the navigation of actually pedestrians. That's why we picked 600. And we wanted the information related to integration and choice. And this gave us graphs with certain informations and numbers that were related to the amount of integration and choice and the segments mentioned in the map. Next, please. And as a methodology, we then attempted to implement the Dextre algorithm, which is the most important part, as this is the tool that we use to actually produce these paths. So we wanted a simple, typical Dextre algorithm that would give us the most efficient path. So how the pursuit goes is that we input the graph from the analysis from the first step, we sort them as lines. Then we assign value of the graph nodes to infinity. We select A, which is the start point of taking the path, and B as a destination point for taking the path. Then we assign values of path destination B to 0, which is a very important step in the algorithm. We initialize search from A, and then we select unknown node with the least value. Then we calculate the old cost of node A and select that node and combine it with their average mean. And the output is actually the minimum amount of line 7, which is it. And this as a result produces the shortest and the most efficient path. Next, please. And now, as a first step, what we mentioned, we're looking into extracting the location of the selected land use from Google Maps API. So Initially, as we had a selected area, we entered the latitude and amount of the longitude, and we tried to extract cafes, supermarket, public transport, and pubs and bars. What was really important in the step for Google Maps API to identify these points for us was to use all kind of the synonyms for the locations that we actually mentioned. And then as a result, we have them. Next, please. So as you see, these are the outputs produced by Google Maps API. So the blue one is actually the pubs and bars in the selected area of study. The cafes are in green. These are actually all the cafes and coffee shops mentioned in the selected area. Public transport stations are the ones that are marked at red, supermarkets at yellow. And as the last step, we attempted to integrate steps from part 1 and part 3 all together in order to have one map, because why? This is the framework that we use for pathfinding and finding those paths that could be perceived to be safe from the virus. Next, please. And now, as a result, as the last and the most important step, what was important was to actually attempt to draw those paths. Now, this is consistent of some subsections. Here, we are talking about the first and second subsection here. Initially, what we do is that we find the start point and the destination point for the path taken, which is A and B here. We draw a search radius between A and B in order to make it ideal to actually find those paths and take those paths. We define the diameter, and then what we do initially is to find all possible paths between A and B regarding the length, regarding all other factors that we have to take into consideration. Next, please. And then after that, we implement our Dextre algorithm, but most importantly, we observe each path in terms of the amount of integration and choice we have. So from the analysis, if you look into the red marks, we notice that the analysis has produced segments and paths that actually have an integration amount between 9 to 770, and their choice amount is between 0 and 14,000. So what was important here, not only to find the most efficient path and implementing the Dextre algorithm, but we're interested in the types of paths that have segments, that their segments have an average amount of integration and choice. So we're looking into a second level of integration and choice. We're not looking to the lowest one, and we're not looking into the largest one. That's why the integration should be something here, in this case, between 200 and 450, and the choice amount should be 5,500 and 8,000 in general. Then here we calculate the most efficient path, and we find that efficient path that actually has the smallest length and has such characteristics. This step may produce 3 to 4 paths normally. Next slide, please. So as it's seen here, we have 4 different paths. And as the last step, what was the most important was to extract all the information from all the paths that we have. And here, the option that would actually allow for producing one final path was actually the amount of its proximity to those selected land use, or what we can actually, in this case, call here locations that attract a lot of people. So we were not in general looking into paths with the most integration and choice, because we wanted the least amount of flow, because the highest amount of flow would actually mean that there would be more people on that path. So social distancing would be very common. And as a result, that would not bring the perception of safety from the virus, because seeing more people will give us more insecurity in this case. And also the last step that would allow for making one path was actually the ones that, as we said, had the least number of attraction locations or land use. And in this case, there was the red path that was the selected one. Next slide, please. So we see that all these steps from 1 to 2 to 3 to 4 to 5 and 6, that initially we attempted to make the search radius between A and B. Then we attempted to draw all possible paths. We then found the paths that could be the most efficient in terms of length. We compared them in terms of integration and choice. And as the last step, we compared them in terms of the amount of attraction locations they had on that certain path. So for example, the path with the least number of attraction location, and with the criteria of integration of choice was actually the path that was selected between that start point and end point here. And in this case is the red path. Next slide, please. So here you can see that actually the algorithm is able to produce a path between A and B with the characteristics mentioned. and with the amounts of integration choices actually designated or defined for them, which is in this case that we can see different paths in different areas of location in the area of study that we have. This is a path that could bring the perception of safety from the virus, but in order to validate that, we had to proceed with the following step. Next slide, please. So the following step here, it involves experimentation and conclusion as an output. This is technically, however, a part of the methodology, but it's a separate section as we no longer deal with the macro scale. We have covered that area. Now we're looking into the micro scale. Next slide. So the experimentation involved testing the paths on, in fact, 24 participants. The participants, half of them, almost half of the number, were female. The other half were male. Over 60% were studying in areas of built environment. The other had other professions or interests. So they were actually defined to follow paths. In this case, we have 4 paths from the 2 different A's and B's. So in this case, we have the first path compared against the second path and the third path compared against the fourth path. The paths that are colored in blue are the paths that are coming from the algorithm, and these are the designated paths, while 1 and 3 are the most popular paths and the paths that have, in fact, the most amount of integration and are the easiest to take as a result. So the participants were actually required to take all of these paths, and as a result, they were required to fill in a questionnaire in order to get outputs from it and to conclude from them. Next slide, please. So at first, before proceeding with the results coming from the participants, we compared all the 4 paths in terms of integration, in terms of choice, in terms of the number of attraction location that actually each of them have, and as a result, in terms of their length. So in terms of integration, obviously path 1 and 3, that were the paths that were the most integrated. They had the highest amount, 2 and 4 had the least. Again, when it comes to choice, path 1 and 3 had the highest amount of choice and the least amount of that. And also in terms of the number of attraction locations, 1 and 3 as well had the highest amount of attraction location compared to the blue ones. In terms of length, there was somehow dissimilar, not so much of a difference in terms of that, because we used an algorithm that was actually trying to produce the most efficient path. That was why we actually attempted to use the Dextre algorithm. Next slide, please. Now, coming out from the results informed by the participants and the people who took those paths, in terms of overall experience, we can say that path 2 and 4, the light blue section, they actually had the more pleasant experience. The other half, they had a neutral experience, and a very small number somehow had an unpleasant experience. And in terms of safety from the virus, also path 1 and 3, they were mostly perceived as neutral, then unpleasant, and last as pleasant. Also, results in terms of the paths, they were compared in terms of safety from the virus, in terms of their efficiency and ease of navigation. And of course, not as part of the study, but based on appearance-based syntax, we also wanted to compare the paths in terms of the perception of safety from the crime coming from the participants. So each of them were also, in addition to being required to answer questions regarding safety from the virus, were actually required to answer about this question to see whether they actually did feel safe from crime or not. And we actually noticed really interesting results. Next slide, please. So as a conclusion, we noticed that almost 85%, they found those designated paths to be safe from the virus. However, in terms of safety from crime, 40% thought that they were not safe from the crime. And this has to do with the designated paths 2 and 4, all of these conclusions. And the reason for that is that in space syntax, we have this famous theory that it says that paths that actually have the lowest amount of integration also tend to be the ones that are not safe from crime. And this kind of coincided with what we had to achieve. However, this applied to only 40%, but this can be later optimized. Also, the existence of even a very small number of certain land use can actually cause discomfort during weekends on certain paths. For example, even if there's one pub in a path on a weekend day, still it can accelerate that feeling of not being safe from the virus itself. And this has to be paid attention to. Additionally, some types of land use were actually the most active, and they had actually the most impact in terms of pathfinding throughout morning times. This actually has to do mostly with locations such as cafes. And last but not least, as the methodology itself was had a probability-based approach, street events cannot be predicted in it, meaning that unpredicted events, unpredicted occurrences, it cannot be actually quantified. And at times that can impact the pathfinding because we're relying on methodology and information that is actually stable. It's not time-based. And as a result, these cannot be predicted. However, these can actually inform the algorithm and can be used in the future.